Hello, everybody, and welcome to this virtual recording for our second fluvial geomorphology and hydrology lecture for the Tuesday, November 26th lecture portion. Obviously, we're doing this virtually because I'm not saying that I don't expect all of you would be here in your seats happily smiling at me, but I suspect that courses or the class would be severely less below what it should be for attendance that day. And this way, you all are subject to some time with me over the Thanksgiving break, which isn't that fun? We get to spend that time together. That's something we can all give thanks for. Now, your suggested reading for this week is your Geosystems text, chapter 14, if you're reading along. And then looking ahead to what we have coming up, your Prelim 9 is open. That is open from last Thursday through the Monday that we get back. So that is, I've changed that submission date to be 11:59 p.m. on Monday the 2nd. Previously it was at 5 o'clock. Also, your lecture quiz 5 was yesterday. If you're watching this on Tuesday, which I assume you all are. So hopefully that all went well. Obviously, we do not accept late submissions for those. So I really hope that you're all able to turn that in. Now, looking ahead, right, we've got our Lab 9 that will be on the 3rd and 4th of December. So that week after we get back from the Thanksgiving break. The following week, the following Monday, we have our Lecture Quiz 6. That week, we have our Lab Exam 2, as well as we're mopping up the last bits of the semester. And then we're staring down finals week pretty quick after that. Reminder that our final is from 1 to 2:50 p.m. on Friday the 20th of December in Phillips 007, where we have our lecture. All right, so let's go ahead and get into the review portion. So just to kind of recap some of the things that we talked about on Thursday, right, we started talking about rivers and how fluvial processes shape the world and how we can start to understand the different ways that we can quantify mechanics within a stream. So we looked at hydrology, and that we defined as the science of water, its global circulation, distribution, and properties. And we looked at the term fluvial geomorphology. Fluvial stems from Latin, meaning river or stream or flowing water. And it's basically looking at how rivers and streams shape the landscapes around us. What is a stream? Well, remember, it's not really a size component. It's just a water flowing in a relatively long, narrow body or channel most of the time. Obviously, it can spill over, and we're going to talk about a lot today the different things that happens when water spills up over its banks and deposits things, makes what we call a flood bank a floodplain or levees, and we'll look at a bunch of different other terms today, and that's really what the focus of today is just kind of understanding the different landforms that the fluvial landscapes provide us. Streams are agents of both erosion and geomorphic work. This is just a still, right? And we looked at this as a video in the last lecture. But in this case, the stream or the river was running through that little gap there, and as it was running through, it was starting to chew away at that bank on the left side of the image, causing it to be undercut, and then through things like mass wasting, fail. And we looked at the different types of stream classifications, from hydrologic to sediment loads to channel patterns to channel substrates and to drainage patterns. Right, so for the hydrologic stuff, right, we're looking at perennial, intermittent, ephemeral, and exotic. Right, for sediment load, we were looking at bed load, suspended load, and dissolved load. For channel patterns, we were looking at straight channels, meandering channels, braided channels, and anabranching or anastomosing channels. For substrate, we were just looking at bedrock or alluvium. And then for the drainage pattern, we were looking at things like we see here on the screen, right? Dendritic, which is kind of looks like a tree oftentimes, parallel, radial, rectangular, trellis, and deranged. Some of those are geologic controls, right? Parallel likely is a geologic control, or perhaps tectonic control. Rectangular is certainly a geologic control. Those are usually following fault lines. Radial is usually along a conical mountain. Deranged, those are typically in places like moraines, which we'll talk more about next week when we get into kind of the glacial stuff. And then if we consider how a stream does what it does, well, you have to look at how much water is moving through, right? It's discharge, it's Q, so the volume of water moving through a stream per given unit of time. We have to look at how sloped the gradient of the stream is. We have to look at how much sediment is available to move. If there's way too much sediment, well, it's not going to be able to do much erosion. If there's little sediment, right, then the stream can try and erode through if it is capable of moving that sediment or entraining that sediment within its flow. And we defined the stream power equation, which is just, that is rho, that is not a P, so Greek letter rho for the fluid density, G is the force of gravity, Q is the discharge, and S is the slope. And then finally, we looked at the different zones of production, and we looked at the longitudinal profiles of just an example stream network, right? So the zone of production is often typified by very steep channel or very channel valley walls. So the channel itself is very connected to the hill slopes. As we move down into zone 2, the transfer zone, we see a decoupling, at least a little bit, of the channel itself and the valley margin, but they can interact and intersect from time to time as the channel is moving about. And then once we get down into zone 3, our depositional zone, sediment is depositing out as the velocity is slowing. This channel is much wider and a bit more shallow relative to its width. And we see things like deltas. Now, we'll talk a lot about those different landforms today. And that's where we're going to start the note portion of the lecture. Now, one quick thing, I am not going to be slowing down for this. I'm just going to kind of wrap this out. So what I would highly suggest doing is, as I'm going through, once I switch slides, just pause the video, write down everything on the slide, then play it and listen to me talking, and then add to your notes that way. That way that if I'm going too fast for you to keep up on the slide, you are just able to stop, pause me, which I'm sure many of you would love to do in lecture, write down everything on the slide, and then move forward and listen to me talk through it. All right, so while we've seen this diagram before, right, we looked at our longitudinal profile. This is a great example of what we would call a graded stream. Now, oftentimes, at least further back in the history of geomorphic research, we looked at things in a very qualitative perspective, right? We didn't have the tools and the methods that we do now to be able to look at things from a very intense quantitative perspective. As such, what that meant for us is that we had to be able to look at and interpret or predict what a landscape would look like based off of our observations. Now, there was a character long back, kind of a very prominent figure in geomorphology called William Morris Davis, and he came up with this thing that we call the cycle of erosion, right? And it's basically how a landform is set up, its initial state, and then how it erodes and degrades and develops over time. Now, a graded stream kind of gets at that cycle of erosion, that Davisian concept that says that a stream is, in a graded state, the stream is kind of at what we would almost call an equilibrium perspective, right? So the stream is able to transport, on average, over a period of years, all the sediment received from the slopes in the watershed. So it's not necessarily changing its shape. So this longitudinal profile that we see here, that we walked through pretty intensely at the end of last hour, or the last class period, was exactly that. We were looking at a graded stream, a perfect system, an equilibrium where you had your zone of erosion, your zone of transport, your zone of deposition. It was fully developed. Now, nature is not that way, right? That's just something we have to understand. We're never truly in an equilibrium state. Equilibrium states exist if you look at things in a very small time slice. Now, we're thinking of geologic time, right? So in geologic time, maybe it's never going to be an equilibrium, but on that very, very small time slice, maybe a human lifetime, then sure, we could say that the system is in equilibrium, perhaps it's graded. But if we look at that much longer timeline, the stream is developing towards something else. It's responding to changes within the lithosphere, within the precipitation patterns and the climatic regime, depending on the base level. So the level that the stream is flowing to, that we see obviously kind of right above my head, right? In this case, the base level is some type of body of water. All streams tend towards a graded state. They never reach it, but they're always developing towards something like that. So the streams can't change their sediment load, and they can't change the amount of discharge in this perfect scenario. It can change its shape or the form of the channels in response to these different perturbations or things that are disrupting the stream. So to do that, it's adjusting its gradient, for example, the length of its channel, all of these things, so that it is adequately handling all of the sediment coming into it over a number of years, and it's exporting all of that sediment as well. Okay. A graded stream is a perfect equilibrium system. Ungraded streams, on the other hand, are streams that are out of equilibrium. These are streams that are adjusting to some type of change in their base level, the very bottom level that the stream is flowing into, right? Okay, so what are prime examples of evidence that we have a stream that is ungraded or out of equilibrium? Well, one of the main ones that you're looking at are typically the ones you see on the slide right here, right? Nick points. So, and I don't have it. Oh, there it is. The bottom right graph, or bottom right figure there, we see the word nick point next to the word waterfall. Now, I technically spell that as K-N-I-C-K-P-O-I-N-T, but here they've chosen more of the American spelling for it. But the idea here is a nick point is a zone of active erosion within the stream. Oftentimes we see that expressed by something as simple as a waterfall, right? So below the waterfall, right, it's at a level. Above the waterfall, it's at a much higher level. That is an indication that something has happened to force the stream to incise. And because that stream has been forced to incise, it's eroding actively through its channel, or in this case, through bedrock, to try and get at a more graded state. Now, oftentimes, that's not achieved quickly. Now, this can be in response to a number of different things. For example, a change in base level drops the mouth of the stream's elevation, and it has to respond to that. There are a series of different landforms that form as a response to that type of thing that we'll talk about a little bit later. But you can have a massive increase of water, for example, maybe an outburst flood of some type from upstream makes water pour through, scouring things out, and then it has to work through all that sediment that's been deposited in the lower reaches. So then that throws it out of equilibrium, and then it has to respond in some way, shape, or form. There are some other key indicators that we have streams that are ungraded, or those that are out of equilibrium. Canyons. So all over the western United States, we see these beautiful examples of what we call entrenched meanders. So entrenched meanders are, as you see it, right, a meandering stream. We see that those big arcuate bends in the river on that bigger picture to the right underneath my talking head. And there it is incised through solid bedrock a good couple hundred feet down to the modern river level. Now, these entrenched meanders form in response to, as you would suspect, a massive change in the base level of the stream. So something has caused massive erosion downstream, and the stream is responding to that, being forced to incise rapidly. Canyons are another great example of that exact trait, right? So here we're looking at the grandest of them all, Grand Canyon, right? And here there was a quick aside, a really cool thing about Grand Canyon, a really fascinating thing is we are not as a scientific community at a consensus on as to how Grand Canyon formed. We're not even at a consensus as to when it formed. Now, the best evidence that we have available to us say the canyon is actually relatively young, on the order of about 6 million years old. And as best we can guess, as at least in the side of science and this scientific debate, which is one of the oldest we have in the community, it seems like it was initiated in response to some type of major lake spilling over a little bit upstream, and that caused the entrenchment of the Colorado River, or the ancestral Colorado River, and it has been incising down and down and down to where it is today. Along with that has become the major thing with the width of the canyon is actually mass wasting. So hill slope failure, we talked about that on Thursday. But it's just a fascinating concept to think that we don't technically know exactly how Grand Canyon formed. There's lots of evidence and suggestions on how. I am, as I said, of the mindset that there's a large lake just upstream from the canyon where we have things like lake sediments deposited, that there's no lake there anymore. That suggests that it might have drained semi-catastrophically at some point around 6 million years ago. At such a time, it helped carve the canyon and kick off the thing that we see today as one of the most breathtaking national parks that we have here in the country. But canyons themselves and entrenched meanders are great examples of these ungraded hallmarks. Now, if we look at the hypothetical development of a graded long profile, so here we're looking at that longitudinal profile. Oftentimes we just call that a long profile of the stream. And this is an ungraded system. So we're going to follow that red line that you see, or that I have highlighted here on this little graphic. In its ungraded state, notice all these little rapids and it says falls, but nick points. All these little breaks in slope, right, that we see as we step down through this little diagram from top to bottom. It looks like there's a bunch of stair steps, right? Now, something happens. Maybe this is maybe the lake itself. So maybe instead of a sea, this is flowing into a lake, and that lake drains catastrophically. Or perhaps we are going into maybe an ice age, and more liquid water is locked up on land. So the base level, the sea, actually falls because more water is finding its way onto land as snow and ice. But something happens where the base level of this river falls out. Now, the stream begins to incise as a response to that decreased base level. Hallmarks, V-shaped valleys are a good indicator of that. Canyons, entrenched meanders, waterfalls, and rapids. These are all very indicative of rapidly incising systems. So here we can see some examples of that, right? We looked at V-shaped valleys in zone 1, the production zone for sediment, earlier on in last week's lecture. But we also see nick points, so waterfalls, rapids, things like that, where the water gets really fast and really choppy. Those are good examples and good indicators that we have a zone of active erosion moving through at a certain time. Now, these are not static. They're what we call transient. They move around. Usually they're cutting their way upstream. It's not, if it's moving through bedrock, it's not really in a time scale that we might see. But if it's moving through alluvium, so right, sands and gravels and silts and clays and whatnot, it's very likely that that is technically something that we could see, but it's so rare to see that because that signal is lost so rapidly. Right, we saw the pictures from the Rapidan Dam that I've been showing you. The river is not flowing at the level it did immediately after the overspill occurred. It is much lower down. It is now almost at the level of the downstream extent of the stream because it was flowing through sands and gravels, and it rapidly cut through all of that. So we don't often see that, but where there's a lot of bedrock, that is a good indicator. If we see things like rapids and waterfalls, that the stream is trying to incise, but it's hung up on something that's harder to erode through. Now, step 3, the stream or the valley begins widening. Think of this, we're kind of working through that zone of production, zone of transport, and zone of deposition, but in a slightly different way. Right? The whole system is trying to do all these things because it's just rapidly responding to this change. So in this in kind of step 3 after base level fall, the valley is going to be widening out. The stream's going to be meandering back and forth. And as it meanders back and forth, it's going to be entraining all of that sediment from undercutting the banks and the hill slopes. And that sediment's going to be moving down. It's going to be building out its floodplain, which we'll see what that is here in just a little bit. And it's going to be kind of making room for itself to go. Step 4, we start to see here really typified that long profile, right? That nice arcuate, steeper on the left, shallow on the right, long profile that we talked about pretty extensively on last Thursday. So here we've got continued excavation of the stream. So it's continuing to cut down and erode. It's deepening, it's widening. The valley walls are being pushed further and further back until we really see those zones start to develop, right? That zone of erosion on the left, the zone of transport in the middle, and the zone of deposition on the right as the stream is coming into that graded profile. Boo. Hi, I got a lot bigger for your screen. Here's the gig. The next slide, I'm going to ramble for about a good 20, 30 seconds, telling you I don't know if the video that I'm trying to play is going to play on recording. After I finished the recording, I looked back and it is not playing. So before you click onto that next screen, go into the link below and you will see the video that I am about to play linked in the description to this YouTube video. Go ahead and open that video up. Put it to the side. Have me on the other side. Listen to me ramble for a minute. And then when I start the actual video, you'll hear me say, oh, okay. And then I'll go blah, 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 blah. And I'll talk about all these things. But unfortunately, because I'm recording and I was playing a YouTube video through the slide, it doesn't like that and it won't record that for copyright and blah, 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 blah. So go ahead and the slide will advance. As it does so, I'll ramble, or at least past me will ramble for a few minutes. And once past me is done rambling for 30 seconds or so, I'll start walking through the video. I apologize. I forgot this was coming up, but I really like the video. It used to be something that I could actually play and toggle, but that they got rid of that and the website went down, but somebody recorded it fortunately so that I could use it in the future, it would seem. Anywho, go on and carry forward. Now, we're going to play a... Uh-oh. I don't know if you guys can see that, but it moved me behind the video. That's fine. We're going to play this quick video here. Hopefully it works. Of a meandering river and terrace floodplain development. If it doesn't work, I will make sure to have the video linked in the description below. At which point, if this isn't playing for some reason, and I don't remember if YouTube will play on recordings. Unfortunately, I don't think it will. Go ahead and pause the video now. Open up the video in YouTube on a second window. And then when you're ready to start playing the video, start playing me and the video at the same time. So that way I'm walking you through what's happening here. I forgot about this part and I really want to use this video. So we're going to go ahead and see how this works. Okay, so here, this is that valley widening perspective, right? The stream is just meandering around, widening its valley walls, building out its floodplain. Now this is flowing all through alluvium here. Okay, now, at a certain point, we can see all of these different features. Oxbow lakes, meander scars, cut banks and point bars. And then something happens where the base level falls or the entire area is uplifted tectonically and it cuts down into its floodplain. That feature that's left behind, that old floodplain, is what we call a terrace. These are alluvial terraces. They're made of alluvium. And then we see things like undercut banks, point bar deposits, and back swamps. Perhaps it floods and leaves all of that sediment from flooding. Then we can look here in this inset box and see as this stream starts to flow up and the sediment-rich water from floods are deposited, we form natural levees. So these are high banks around the river that contains the channel until high flooding events happen. You can see that happen again here. Okay. And there we go. So I don't know if you were able to follow along with that. I'll have to check back in the recording. If you weren't, just go ahead and make sure that you watch that with me talking over it at the same time. Okay, moving on. Hopefully that wasn't a weird technical thing. I don't remember how that works. So here is just kind of a static version of that same graphic that we were watching. And we're going to walk through these different landforms that you see here, and we're going to put some context to what all of these names mean. And that's going to be most of the rest of the most of the rest of the lecture here before I let you go. Now, the first one we're going to talk about is a floodplain. I've used this term a few times, and we're going to kind of define it, look at some examples, and go through them. Now, a floodplain very easily is just the low, flat region of land flanking a river. In normal conditions, as we see in the graphic on the right here, that entire thing, that low elevation, basically immediately above the river, is all part of its active floodplain. Now, a floodplain is inundated by floodwaters. It's that region that, as you have maybe here your spring meltwater or larger floods, it's the zone that's constantly getting basically buried underwater or dunked underwater when these big flood pulses occur. Now, it is formed because as that river is widening itself, its margins are pushing further and further back. It's all immediately above the river. It's at that same or roughly same elevation from that immediately next to the river all the way over to the valley margins. So as the stream is making more room for itself, it's handling that floodwater more and more and more. Now, obviously, I don't want to risk anthropomorphizing the stream or giving it human tendencies. The stream doesn't want anything, but what the stream is doing from a physical perspective is widening its valley margins, and as the floods are coming through, they're dispersing over a much broader area. And if they're dispersing over a much broader area, then the velocity of those floods are slowing down and it's not nearly as erosive. So this is just a typical progression as stream systems develop. So something also important to note is that higher velocities, as we talked about when we looked at the Hillstrom curve, are able to move and then deposit coarser material and vice versa. So as the big pulse comes through, if it's a really big flood, it can entrain really big things. But those things are going to fall out very quickly. And it's often the case that they're not transported very far. Now here we can see some great examples of an active floodplain. We're right next to one. In the spring, if you've been here for a couple of years, you have seen that feature right under the footbridge on the Haas side of the river, completely underwater. If you're new, hold tight. I'm sure you'll see it before you graduate. Now we can look at a couple of different examples of these different stages of kind of the floodplain itself, right? The first one would perhaps be the inner berm. This is, if we're looking at the graphic on the left-hand side here, the inner berm is kind of that lower position that the channel is contained within. Now, as floodwaters start to rise, they are contained within the bankful stage. Now, the bankful stage is kind of the maximum height within the active channel of the river that water can be contained within. If it flows above that, then we get into what we call flood stages. Now, flood stages are just those stages when you're above the bankful height of the channel and water is spilling out over onto the active floodplain. In this case, there are times, if you were around, goodness, I think it would have been the spring before this. So spring of 23. Yeah, spring of 23 is when that bottom picture was taken from. We had some very intense floods on the Chippewa and throughout the region. In response to a few different things, we had snow, and then we had what we call rain on snow events, which is, yes, as obvious as it sounds, it's rain falling onto snow. So you get rapid melting of the snow and then a huge pulse of water moving through Instead of just that you get from the rain. And when there's frozen ground, there's nowhere for the water to seep into. It just rushes off and rushes into the nearest stream or river. So that's kind of what you're looking at, right? From the point bar above to the flooded Chippewa below. This is an example of the active floodplain of the Chippewa River. All right, the next one we're going to look at is right here. This is not, we're not specifically looking at the cutoff. It's not the cutoff, but we're kind of looking at the point bar. We're kind of looking at the cut bank, this kind of progression here. So we're going to learn some new terms. I think you might recall, perhaps when we talked about the tectonic settings, when we talked about normal faulting, and we talked about the terms Horst and Graben, right? These are strong German words that I think I mentioned we're going to be learning a little bit more German, and here that is, the Thalweg. So the Thalweg is the deepest part of the channel. Now, as the stream is flowing around these bends, the deepest part of the channel changes its position. Now, if you're flowing along the cut bank, which, let me see if I can, I think if I draw this out, the cut bank is over here, right? So that's the side of the river that the river's cutting into its banks. Cut bank, right? It's kind of an obvious term, a little too on the nose, but easy to remember. So this is usually on the outside of a big meander bend. So the features that you're looking at are a series of meander bends. Now, along that meander bend is where the stream, if we look on the top left, right here, right? So that is the zone where velocity is the highest. We have flow moving around that bend, something we call helicoidal flow. So that's basically flow doing some loop-de-loops like that around the exterior walls of the meander bend, and that is working to undercut that bank. And as it undercuts that bank, right, it's adding sediment to the system. It's working through its floodplain. Now, then, as the river transitions and kind of straightens out again, right, you can see that on this area right here. As it's flowing through kind of a straighter perspective, right, the Thalweg is located in the middle of the channel, not on either banks. So it moves, it alternates. Now, if we look at the cut bank side again, whether we're looking at the top right one here or the one on the left over here, we have two features that we need to consider. There's the cut bank, which is the erosional landform on the outside of the bend, and we have the point bar, which is the depositional landform on the inside of the meander bend, and we see that right here and over here. I hope these are drying as I'm recording. I believe they are. So these are really useful to us because we look at these connections, and oftentimes, as we have meandering rivers, these kind of alternate between, at least in the very sinuous or bendy regions of the stream, they alternate between cut banks and point bars and cut banks, and that's exactly what you're seeing here. Is this alternating between the cut bank and the point bar and the cut bank again. Okay, so as the stream is cutting into its bank, it's depositing on that interior side, the side where the point bar is. So in this case, if we're looking at least at the bend closest to me, the one that my head is nearest, the stream is cutting into its banks that way, and it's depositing on the interior of the bank over here, right? That's our point bar. Point bars are often made of sands and gravels and silts and clays, all these other materials that are being deposited here. Now, part of the reason is because that's a low flow zone, right? So the maximum velocity is located along the edge of that meander bend. As such, this is a low flow and low pressure zone. So in these cases, sediment is allowed to settle out. So as it eats its way into its banks, it's depositing sediment on the inside. That's just one of the ways that the stream is handling its sediment load. And here you can see a great prime example of exactly that, right? So here, right next to my head, right, we've got a point bar there and a big cut bank right here, right? And then we've got a point bar on the inside of this big arcuate bend, and we have the cut bank right there. We've got the point bar here and a cut bank over here. We've got a point bar here and a cut bank all the way coming through on this bend here. All right, this is on the within the Blue Earth Le Sueur River watershed, which is over near Mankato, Minnesota, which is south of the Twin Cities metropolitan area, about an hour or so. And this is a very sinuous, very meandering river that's working through a lot of different sediment. This is actually a little bit upstream of the Rapidan Dam area that we've seen a few pictures of. All right, the next one that we're going to look at are these guys over here, oxbow lakes and meander scars. Now there are different terms for the term meander scar. We'll look at a couple of them here, but these are relics. As the river is migrating and changing position, we see these meander scars, or scroll bars, as the other term is for them, deposited all over the place. And we saw that graphic, the GIF, when we were looking at the meandering channel, right? It was that very red GIF where the river was moving back and forth through the years, making all of these oxbow lakes. And I might have that coming up here in a second. I don't recall. But here you can see a beautiful example of meander scrolls. Now, as the river is migrating, so in this case, let's look at this section of the river over here. So the scroll bars, as the river is migrating, it's moving this way. So the river is cutting into this bank right here and depositing on this bank right here. We can see that point bar pretty evident. Now, as it's doing that, as it's migrating like that, we can see these meander scrolls here follow that migratory path of the river as the bend is extending further and further to, in this case, the northwest. So as it's migrating, we see those those scroll bars as relic point bars. So that's really what they are. They're kind of point bars that, as you have floods and overbank deposits happening, which we saw, or you would have seen in that YouTube video earlier, those are being kept and maintained. Lots of times we can actually find trees growing on them. They're a little bit higher up. They're not impacted as greatly from floods, and once the trees start to take root, they can actually help us understand the migratory rates of these different rivers if we don't have satellite imagery to see them. Because you can look at each of those trees and you can core trees on each of those scroll bars. So each, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, maybe 12. Yeah, there are 12 scroll bars there. So if you core the trees and count the rings on the trees on each of those those scroll bars, you can actually see the rate, because you know how old the tree is, and if you know how old the tree is, you know how long the tree's been growing, and you can make some assumptions there. You can see, okay, well, how long did it take to get to the next scroll bar and the next scroll bar and the next scroll bar? So that's actually a useful tool for fluvial geomorphologists to understand how these systems are moving and changing. It's not always perfect, but it is one indicator that we can have. We can see another example here. These are highlighted in what we call a digital elevation model. So this is just a digital model of the surface. So these scroll bars are forming when the channel is widening, and that widening occurs near the meander bend apex. So the new scroll ridges are deposited along the inner bend of the point bar. We talked about that on the last one, but here are the things that I said on the last one for you to write down. There we go. All right. The next thing that we are going to look at is right over here. So we are going to look at an oxbow lake, and we're going to look at cutoffs. So oxbow lakes are really just meanders that have been cut off for some reason or another. Um, so here we can see a good example of what that looks like. So we'll walk through this graphic, right? Step one, and I would suggest writing down these steps and taking note of this. This is definitely something you'll want to understand and know when we move on for the quizzes and exams and whatnot. So step one, we have this big meander bend forming, and we get what's called a meander neck. So the neck is basically the distance, or that zone that is pinched between two meanders. So in that step A there is our meander neck. It's just that thin region between the river and between that bend. Now we have another meander neck right here. It's just not labeled in this particular graphic. So here we've got a point bar, a depositional region here, but then it's incising into this neck. Now, if the water is flowing downstream that way, right, it's cutting into this bank right here, and it's flowing around and flowing through its banks, and by the time it gets to the other side, it's also cutting into this bank here. So that neck is getting thinner and thinner and thinner over time as the river is incising into it. Now, if we look at that graphic on the right-hand side, the one that just shows the channel from the top-down perspective, we can see the zones of erosion, and that third one down here and here, that red coloring. And as the neck continues to narrow, and perhaps in response to one of two things, it can be in response to floodwaters raising up over the banks and flowing across, and in that case, we would call that a chute cutoff. And a chute cutoff is water's, risen up. The water level is risen up and is flowing across that level, and it's shooting. Of course, it's not spelled S-H-O-O-T. It's like a chute, C-H-U-T-E, chute. Chutes and ladders, for example. And it is flowing across that. Now, the other way it can happen is through a neck cutoff. And a neck cutoff is exactly as it sounds. So the river has incised into its neck so much that there's barely anything left. And at some point, the walls crumble and the stream is able to work through that new cutoff there. And as it does so, the gradient through that reach, through this area right here, is substantially steeper than the gradient of the water flowing around that whole way. So it will start to erode that new cutoff, or that zone, much more rapidly. So water will then start to flow and preferentially move through the cutoff rather than in the path that the river had previously been going. And because those zones, erase here, there we go. Because the zones right here and right here are not receiving the same amount of water, they are lower velocity. And because they're lower velocity, they're zones of low pressure. So sediment is able to deposit in those zones enough to essentially form new levees. And what's left, the relic feature, is an oxbow lake, right? That cutoff lake is what that is right there. That's an oxbow lake. Now, we have an oxbow lake here in Eau Claire. In fact, I'm sure many of you have been to it, driven by it, or live near it, and that is Half Moon Lake. That is an oxbow lake to the Chippewa River. Now, here you can see in real time, well, not real time, but you can see oxbows forming all over the place. And the Rio Mamoré, this time lapse that we saw earlier, right? So one really prominent one, I'm just going to circle it here. You can watch it happen. Let's see if there's another one that I should. That one's a good one to watch. So watch as the river, that neck is narrowing, it cuts off, and then what's left is that big arcuate stream path there. And here you can see our very own, right, Half Moon Lake is this feature right here where Carson Park is. And the Menards Tennis Center is right there. There's actually a brand new boardwalk trail that goes from behind the tennis center, walks along here all the way over to Rod and Gun Club Park. I highly recommend it. It's very well maintained. It's a beautiful trail, and it's just kind of a nice, fun walk that, if you live down in the housing down by Water Street and whatnot, it's not that hard to get to, and it's a nice time. And obviously the Sonoteg Center is right here, just so that you can orient yourselves. And we are right over. Nope. Just right there. There we go. Ignore that. Get rid of that. Awesome. All right. So Half Moon Lake, that is a primary and prime example of a meander neck cutoff that has turned into an oxbow lake. All right. The next one that we're going to look at here, they term bluffs. Now, in this case, it's bluffs, but we're going to call them something different. We're going to call them terraces. Now, as I've said, go ahead and pause so that you can write all this down. And when you're ready for me to continue yapping, go ahead and unpause the video. So I will sit here for a second, awkwardly waiting for you to pause the video. All right. I'm assuming that you awkwardly stared at me for a second, waiting for me to move, wondering if I had actually just stopped moving, if things froze or not, but I rest assured I was just waiting. Now, if we look at terrace development and formation, this is the general trend that we see. Now, there are a lot of different types of terraces. We are going to observe a few of them here. One of the more prominent ones are aggradational terraces. Okay. Now, an aggradational terrace, when something aggrades, its elevation is rising through deposition. So the terrace itself is just the level left over when a river has incised into its floodplain. So if something causes the base level to fall and it's already built out a nice big floodplain, it erodes into that floodplain and starts moving around again. Well, that flat planar surface, that's what we call a terrace. We have them all over the place around us. We'll look at a couple prime examples. I'm sure some of you currently live on a terrace. You just don't know it. Now, an aggradational terrace is what happens when the valley fills up with sediment and then the base level falls, or perhaps the amount of water moving into the stream increases, or the amount of sediment moving into the stream decreases, allowing the river to incise into its valley. Into the alluvium that it is filled up with. So this is going to be, if we look at that top example there, perhaps fill 1. So lots of sediment is moving through the system. The river aggrades and aggrades and aggrades up to a top level. And then something happens to cause that base level to fall. And it cuts into that surface. And then it fills back up again when sediment supply is enhanced. And then base level falls and it cuts again, and then it rises again and it cuts again. That's exactly what you're seeing from aggradational terraces. We also call these fill cut terraces, F-I-L-L, fill cut terraces. So it fills up and then it cuts down. And as it's cutting into it's leaving those relic surfaces, those previous floodplains, as evidence to the level that it was aggraded to. The next one that we can look at is called a degradational terrace. So there, perhaps it's moving through bedrock or something similar, and it's cutting down and it's able to work through, and it's cutting down and it's able to work around and it's cutting down. So there, instead of it aggrading and then cutting, it's just at a level and it cuts down and it cuts down and it cuts down. Usually, as I said, this is when base level falls and it's eroding onto some form of bedrock. We also call these strath terraces left over. Now, there are also, we can look at whether there are paired terraces or unpaired terraces. Now, a paired terrace is just a way to describe a terrace where the tread, so that flat surface, that flat sloping surface, matches on both sides of the valley. An unpaired terrace is one where it does not match on both sides of the valley. Now, this can be indicative of a few different things. So for usually you would expect like, oh, well, the river's cutting down and it's moving back and forth and it's developing its floodplain at each of those levels. And that's why you would expect to see these stair-stepping paired terraces. Now, an unpaired terrace, imagine this, right? The river cuts down and it's moving back and forth. Well, on one side, it moves really far to one direction and wipes that terrace out. And it just backs into the valley walls itself, and then it comes back the other way, but it doesn't quite get there. And then maybe it drops a little bit, and then it cuts into that terrace, but it doesn't cut into the other side. So you get these unpaired sequences as the river is responding, and what's left over is this variety of tread that just doesn't match on both sides. Here we can see some beautiful examples of just alluvial terraces here, right? So it's not difficult to see, like it's nice flat tread here. It looks like there's another level right here, and then we have the top surface here. So we go from 1, 2, 3 levels, stepping down into the modern floodplain here. On this other image, right, again, nice big flat here, maybe some preserved relic terraces up here, another one right here, and perhaps something right here, and then we're down on the active floodplain. Right, so we can see those nice stair steps down. As I mentioned and alluded to, you live next to or on a terrace. The Chippewa River is full of them. If you live on Upper Campus, and very clearly this is an old picture, how can we tell? Well, we don't see suites, and there's still tennis courts and basketball courts, which is what used to be where suites is now. Catherine Thomas and Putnam are the two dorms that are still standing on Lower Campus where the current science building is being constructed. I don't think, yeah, oh wow, this is really old because Davies is not there, but Old Davies is. And then Centennial clearly isn't there either. So, wow, this is old. I might have been here at this point, but I think this was probably a year or two before I even got to Eau Claire. But that top level, if you're living on Upper Campus, I digress there, is the Wissota Terrace. So this is the top level of the fill terrace of the Chippewa River. Now, if you are on campus, right down here, you're on another terrace, and that terrace pairs to the Randolph neighborhood. I always called it the student ghetto, right? The area where most of the student housing is, and the Third Ward area as well. All of this is the same terrace. This is not on the active floodplain of the Chippewa River. Owens Park is, so over here, and then kind of this area right here. This is part of the active floodplain of the Chip, but here it's moving through these, basically through these terraces. Now, remember what I said, right? If we see riffles, that's a good indication that the stream is actively incising through its bedrock. And I don't know about you, but if you look right here, that's exactly what you're seeing, right? This is a nick point or nick zone on the Chip. It's moving through bedrock right here. It's trying to erode through that. Now, the channel deepens on this side of the little gravel bar, kind of over by the, it'd be like the nucleus and the pickle, and other despicable places like that. Don't ever go there. But it's still working through this. So this is a zone of active erosion as the river is incising down to the level that you would expect down here. There's about 35 meters between the Wissota Terrace and the modern day Chippewa River. So it's moved through a lot of sediment as it does so. Okay, here you can just get another beautiful view here. There are a few more terraces. They're kind of hard to see here. I believe there's one relic up here, and then you kind of get down onto the downtown area. This is all kind of the same level here. Right, and if we look here at this example, from A to C on the left, you've got it eroding into more complex terrain, widening its valley margins, and getting to that point on C on the bottom left image, where it's got this nice big broad floodplain. Well, now we're picking up from here, and then we're going up to here, right? You can see it cutting into that alluvial fill. All right, now we are going to move on to natural levees. We'll look at this very briefly. We saw an example of that earlier, but here with a natural levee, these are just overbank deposits. So as the level of the water is rising, it's spilling over the banks of the stream. And as it spills over the banks of the stream, the velocity is slowing. And as it does so, sediment is settling out. And as it settles out, it forms these natural levees, these, depositional features on the channel margin. So here we can see just kind of a good example of how that works, right? So before the flood in A, again, I would write this type of stuff down. Same thing for the rest of this lecture. You have flood stage water levels, and as they flood, these zones here and here are low pressure, slow flowing zones, and those slow flowing zones inhibit water moving through and kind of increase the depositional rate on those channel margins. And as they do so, they create these nice natural levees that are built up through oftentimes, annual floods. Now, sometimes you can have those levees break. And when you have those levees break, the water spills out over them, dumping tons and tons of sediment. And we call that, kind of fun term here, a crevasse splay. And that crevasse splay is what happens when the river spills out and breaks its levee, and all that sediment and water rushes over the edge there. And you see this big sediment tongue is deposited after that levee has been breached. All right, we're almost to the end here. The next one is an alluvial fan. And now there are some spectacular examples of alluvial fans if you go to the desert Southwest. Death Valley, for example, has some of the most typified alluvial fans in the world. We'll see some pictures here in just a little bit. But alluvial fans are mounds of coarse grained sediment. So oftentimes you have what we call a feeder canyon. So here's our canyon, right? There's a stream flowing through it. But as it flows through it, and it's restricted to the canyon walls. Well, once it gets out of the canyon and has a chance to spread out, once it spreads out, it's not concentrated. So the velocity slows down as it's spreading out over a much broader area, and it's depositing that sediment over that broad region. Now, these are very typical of mountain ranges and the margins of mountain ranges. So when you're coming out of the mountains into a big, broad, flat valley, you'll often see these types of alluvial fans. They have this semicircular radial pattern. On the next picture, we'll look at kind of how they grow a little bit. But they thin, so the thickest portion of the alluvial fan is going to be near and right at the mouth. That's also going to be the steepest portion of the alluvial fan. And then by the time you get out to the very outward margins here, it's a very, very thin lens of sediment that exists until it peters out to nothing. Now, sometimes you can have a bunch of these feeder canyons. So perhaps this was a canyon over here and it was making its own alluvial fan that we can kind of pretend that we see here. And those fans start to coalesce and on-lap onto one another. And we call those bajadas. So those are just a series of coalesced alluvial fans. Here you can see some prime examples of alluvial fans in the Badwater Basin. So I think this is the Badwater fan right here in Death Valley. Another one in Death Valley right here. This is actually one that when I was a PhD student, we actually did a project trying to map out, and sadly I didn't get to go to this one, but we were able to do a project mapping out the different ages and levels of this alluvial fan. Now, the brighter portions that you see here, for example, and all the way over here, and we see it's playing out over here. The brighter portions of the fan are the most recently deposited portions of the fan. Now, it's not always rushing out and flowing over the whole thing. There are depositional channels that move with time. You can see that on the big image as well. You know, here, these are newer portions of this alluvial fan on that really big one that I'm showing you there. These are also younger channels cutting through older material, right? So you can see that on that bottom left image, the oldest material is going to be this kind of preserved little terrace within the fan here, and then over here as well, right? And then the lighter colored regions are the younger portions of the fan. All right. Now, the other depositional landform that we can look at is a delta. We've talked about deltas a little bit. We talked about the Nile River Delta, right? The exotic stream that is the Nile River, flowing from more of the humid regions through the desert into the Med here. So in this case, a delta is just formed when a river enters a body of water. The velocity slows, all that sediment settles out, and it forces the river to kind of split up and into what we call distributaries. So instead of tributaries, which are where two rivers come together, distributaries are where a river splits into multiple channels. And again, just like in alluvial fans, the depositional lobe shifts over time. Now we can see on this top example here, right? So the picture that I have above my noggin, this is maybe the earliest of the fans or portions of the deltaic fan to develop, and then perhaps it moves over here, right? And then 3, it gets over here, and then 4, it splits up and moves over here. And as it's doing so, new land is being created and onlapping onto one another until you get a form that looks like the Nile River Delta that you have. Or sorry, this isn't the Nile. This is oh shoot, this is a fan in Russia. The Nile's coming on the next one. My mistake. Deltas. It's hard to keep them all straight. But we can see here this is exactly what we're having happen. All that sediment is being deposited within that fan and all these different lobes. Now, if we switch over here, right, we can look at a few different deltas. One we often don't think of is the one right in the middle of a continent, the Okavango Delta in Africa and Botswana. There we have the Okavango River, boom, making that beautiful deltaic landform as it's flowing out onto the savanna. We see the Lena River Delta here. We see the Nile here. And we see the Bird's Foot Delta, a very typical feature. One of the best examples in the world of a Bird's Foot Delta right here around Mississippi River. Right? So, as you are working through, you are expected to, if we talked about it in the lecture, if we talked about it in the slides, obviously that is something I will be trying to put out some study guides here before too long, just to help people think about it and kind of organize their thoughts and organize their notes. But we've had fun with rivers. Rivers are my jam. They're one of my favorite things to study in the world. But we're going to be moving into some pretty cool, get it, ice, pun intended, cool landforms next week once we start talking about glaciers. We'll talk about continental glaciers and alpine glaciers, and continental glaciers are usually big ice sheets that form and flow out from a central position, whereas alpine glaciers are those high up in the mountains that form and flow through. We'll talk about all the landforms that they create and all the ways that we interact with them still on a daily basis, because we are in a previously glaciated environment and we've lived there. If you've lived in Wisconsin or Minnesota, you've lived there most of your life. So we'll learn more about that next week. I hope you all have had a wonderful holiday, and I will look forward to seeing you all on Tuesday. Have a good one, everyone.